Hello, everyone. I hope that the lunch was okay, and let's start the next session. And our first speaker is Balázs Indig from the Eötvös University, and he's going to speak about large language models.
Okay. So everybody's up, awakens. So there will be a brief introduction into the field of linguistics. I will talk about the number of words in the language corpus and the related problems that forces us to use GPUs and language models. And I will introduce the pieces of the large language models from our perspective. And then some downstream task that is used by us and has been utilizing large language models. And finally, the issues that we facing currently from our perspective. So language models are not just language, but other fields. But I'm a linguist and a computer science engineer. This is my background. And I have seen many different projects. For example, I've been working for the Hungarian GPT project with the OTP bank. And I've been doing web harvesting to gather large corpora for these language models. And I've been doing pipelines and tool chains to process language, especially Hungarian language. So there will be some Hungarian examples to highlight what the current problems with our languages from the language model perspective. And my research interest is the linguistic patterns of corpora in a data-oriented manner. So this is my avatar made by Natabara, my colleague. It was prompted as the strict Taoist Chinese teacher in a paper collage style, which I think very good resemblance of me. And it demonstrates that not just text can be handled by language models, but all kind of data. And this is the trick when language becomes data, and linguist doesn't like this kind of processing. But what they really do, what we are doing as research, linguistics has been a long road from philosophy to becoming a science. And Chomsky, Noam Chomsky had as a generative linguist who invented the generative grammars. You may know it from programming languages, and it's used everywhere. He's concerned with the ideal speaker-listener relationship, and he liked to prioritize competence where the language is unaffected by irrelevant conditions like memory limitations and noise and all kind of stuff that engineers love so much. And all these problems are the field of performance, which is somewhat ignored by linguists. But a fun fact is that not all linguists are generative linguists, and there are. I'm working currently with functional cognitive linguists, and they really hate the generative ones, and there's plenty of other disciplines, but all are concerned with the ideal conditions, ideal language use, ideal speaker, ideal stuff, because they don't like to say that, because this would make them as a whole a common ground, because they can't imagine the noise that are in corpora, what kind of noise and what kind of errors and other conditions are really in corpora, and they like to think that this kind of errors does not exist, and it's really an ideal condition from the engineering point of view. So there are 5 shades of linguists from my perspective. The theoretical linguist who invents their own examples from intuition, from their reading experience, and they like to talk about their theories, how this and that construction should work, etc., etc. And there are the other one, the corpus linguists, who like to do the same, but they try to find examples to understate, to support their idea, and the absence of examples to be better than the theoretical linguists, because they have experience and experimental results on how their language is really used, and which are the frequent phenomena and which are not so frequent, so doesn't really matter. There are the computational linguists, which I think I am a computational linguist, where we build tools and resources like corpora and other software to formalize and process language, and to support these theories and make new discoveries with these formal tools. And they are some in some way they are rule based, and there are machine learning stuff in it. So it's very diffuse, but the main goal is to help corpus linguists to level up and use computers more, and discover new ideas with computers. Currently there are not so many natural language processing people. They did the classic machine learning stuff in the border of linguistics and data science. Now they are extinct in my view, because they became data scientists or went back to computational linguistics. So because machine learning is out of fashion, and now the large language models are the state of the art. The data scientists are partly these people, but they do not do linguists. So data can be textual data like language, or any other textual data like biological data, or can be signal data, or pictures, or audio, or anything like that. So it's more like data, and not language in the sense that linguists want to see it. The dynamics of these people are something like that 20 years ago, Hungarian computational linguists gave a lot of tools to the world, like you may know Hunspell for spell checking, and there was other good tools. I call this era the rule-based era, where every tool was rule-based, and we Hungarian people could invent better rule-based tools that can solve even the Hungarian morphology and other language-specific stuff computationally, and of course it worked for English and other languages too. So we did state-of-the-art things. About 10 years ago, there was the hybrid era, where NLP was lagged behind 5 to 10 years from the state of the art, and now there are more lagging because the large language model and only the extremes remain. So theoretical linguists are far behind the state of the art, and data scientists doesn't really care about language. So what is language? Language is something that at least 3 native speakers can agree on. The more is the better. And everything below that is in an approximation. There is a passive language use of a single speaker, and this is an approximation of the real language because 1 or 2 people can modify each other's opinion, and there must be a tiebreaker, third one, to define language. Active language use is a subset of passive language use. We know many words, many constructions, but we don't use it always. There are frequently used and not so frequently used words and construction. And from these, when they are captured, they are in corpora, which is an approximation of this active language use. And these corpora are sampled for different phenomena by the corpus linguist. And from these corpora are also built the vector embeddings and the neural network representation of words or subwords to approximate something that is in the corpora that should be language in the best case. So does it matter that how the vectors are created if they are only an approximation of the corpora, which is an approximation, and so on and so on, and it's far from the language, and we doesn't know anything about this approximation? It really does not matter because it works. For the engineer, it's perfectly okay, but for the linguist people, it really matters, and there are people who try to explain these vectors, but in the current state, they don't came up with a good solution that is accepted by linguists. So the number of words in the corpora is a very popular question. How many words in the corpora? How big are the corpora which are in words or tokens, which are the large language model are from? The size of these words called the lexicon. And fun fact that not just the words creates language, but the constructions which these words are put together. And the thing that holds all the constructions as a lexicon is called a constructicon. And this is a very popular field of linguistics today, as many realize that there are much fewer constructions than words in corpora. So it's much more suited for linguistics. There are 28 to 32 grammatical cases with 1 to 4 arguments in the sentence. You can multiply it up, the combinations, but still only a few thousand. There are 1 or 2,000 different combinations that can be examined in this corpora, and it's way fewer than, for example, János Arany's legendary number of words that he used. It's about 1,600 words, and it takes about 60 forms of these words. Most of them are appearing only once, but it's an order of magnitude higher than the combination that may exist. It's funny thing that for one dictionary entry, the 16,000 words, there could be many word forms. There is an interesting link from Tamás Turányi, who is a chemist in the Budapest the BME, and 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 he states that there is 570 possible forms of a single dictionary verb, and this is very high, but it's perfectly possible. But if we add some more information, that we can define new nouns for every concept that we can point at, that this should be noun called, I don't know, some noun, and this noun could be transferred with affixes to verbs, then every noun has also this much of forms, because it can be a verb too. And practically this means, this relation is reversible. So practically it means that infinite number of words exist. Just the question is which of them are used actually. So the challenge is to represent the relationships between them. And for example, with a single precision, 4 bytes for each word, calculating an all-pair shortest path for János Arany's words, that would be 15 gigabyte of RAM, which is in the GPU RAM. A few years ago it was very much, but today it's mostly okay. So, but this is just János Arany's words. But in the corpora, there's so many other words. For example, if you could read 24/7 all year long for 100 years, with 250 words per minute, which is an average reading speed, it would be 15 billion words. 15 and 12 zeros behind it. So this kind of corpus is considered today a small corpus. It's not very large, but from the human perspective, it's very large. And in the Hungarian Web Corpus 2.0 by Nemesky Dávid, my colleague, which has 9 billion words, have 100 million distinct word forms, which is much more, 2 order of magnitude more than even János Arany's words. So this is the problem. But this is because there is a lot of noise in the corpora and non-words and other factors that is not considered an ideal condition for words. So one must somehow approximate, because this much of words can fit in to the GPU's RAM in the raw form. So linguists say that count or not count, there is no such thing as approximation, because we approximate so much from the language, as I said, to the corpora, that making one more step of approximation is unfeasible, and it won't work. So enter data science and problem solved. But as the paraphrase tells, I have a feeling we are not doing linguistics anymore. It's called something else. And how we approximate words and their parts. There are typical features that are used. The linguistic features are suffixes and prefixes. A word should be like something like a prefix, and a stem that could be a compound word of more words, and there should be morphemes behind it and inflections and something like that. And this should reduce the number of distinct words. But there is no an experimental proof of its validity and its language independence. It's something like an imperial standard that should be used for every language. And for most of the word classes like nouns and verbs, it works, but the others, the not so frequent ones, for them are not so good. There is the old school variant for the natural language processing one, the engrams, which there is an example. The word karakterek is there, and it's invented by Shannon with the information theory about 100 years ago. And there is not much younger variation, the workpiece model, which is, I don't know the current one, or it was the current one a few years ago, but the original idea was invented in the 80s, so not so young idea also, but it works. It cuts the words between the spaces and use variable lengths of if its parts by statistic sampling, and it enables the intelligent handling of unknown words and suffixes. And this is an example where karakterek, számítógépek, telek could be splitted to karakter, számítógép, and tel. And tel is not a word, but it could be tail, which has a plural form telek, but it also possible that telek is the land where you can build the house. So this disambiguation should be done on context, and this is what really large language models do. The main goal of this splitting is to reduce the size of the dictionary to the point where it fits the GPU's memory, and then we are okay and make some weights, and we are done. When the model is precisely weighted up, and the algorithms can operate very fast on them. So the simplification is very important, because this system can be very complex in a few steps. From the linguist perspective, it's something like this. If they look at the formulas that you physics do, they see something like this, and if they group the emojis, then it's called emoji analysis in South Park, and it's an allegory of data science and machine learning in that series. So how these language models are built up, what's their pieces? There is the corpus, the most important piece of these models. There was a definition of a corpus, which can be read here, where spoken and written linguistical data, and not necessarily whole text, and maybe it has some metadata, bibliography, annotation, and so on and so on. Nowadays, this is not really true. Only the duplicated amount of text matters currently. It's a pile of text. It's called pile of text because there is a format called pile which has the necessary metadata and all the stuff that needed for language models. It needs much less information and much more text than the old school definition of corpora. Margaret Thatcher has a famous phrase that watch your thoughts, because what you think that will be said by you, and what you said that will be done by you, and what you do that will make your destiny. And this is how your thoughts become large language models. This woman know it before large language models. If you write something on the internet, that it became a corpus, and it became a large language model in a very short time. So the rhetorical question is that if there is a large noisy data set which the searches only affect a small subset, and the larger part of this corpus never actually used, this is called precision in the engineering field. It can be good, but we cannot not actually get recall so good. Then it's worth it. It can be called big data if the biggest part of the data is not really used. It's something like gold panning, when you move a lot of mud, and there will be this amount of gold at the end, and it's worth it. So I used to say that we are in an age which controlled by DJs who used to say that, come on and make some noise, and therefore noise are created on the corpora. Just the size matters. So how a language model is trained? Something like this. It's called the cloze test. It can be familiar from when you learn a foreign language. There are gaps in the sentences, and you must substitute with gaps, and you know the language if you can substitute these words well, and this is how the language model know how to substitute things in sentences and make an abstract thinking of how this model should use language. So the question is that if we mask about 15% of these words, how good should be, how good a random people should perform on this task, and the answer is that if a random word is taken out from a sentence, humans can achieve about 30% of good answers when they know the length of the word, but they are much better on making guesses that semantically correct. It can be accepted, but not the word that is really sought for that sentence, and this make a problem for language models also. But I think it's already overcome. So it's an old problem from now. In the BERT model, which was popular in the 2018, it came out. It also has 30% performance in this task, but have not so good guesses as humans. Nowadays, language model may be far more better on these tasks and far more larger. So the linguistic question is that what if we align these gaps that has the same word, but we don't know the exact word, but we know that it should be the same word under each other. It's called concordance in lexicography, and it's very interesting how it's applied on different fields. And another question stems from this, that what if we don't know that word, but just the context of it, and we have many contexts. Can we guess that word from the many contexts, and can we find the word that fits in all that context? And this question was made by an unknown morphological worker in 2000, and they created a language game when you can ask for a sentence where you don't know a word, but it's only its length, and you can make tips and guesses, and if you you like, then you can get more sentences which might help you or much or not, or most likely it won't make you closer to the solution. I have re-implemented this game because I find it very useful to test humans, how different words are handled in their human language model, in their wetware, implemented in their wetware. So it's very funny to experiment with them. The interesting part is that in this example you have both the left and right context, but if there is no left context or there is no right context, some words can also guess, but some others need both context, and this is the open linguistic question, that why and what's the difference, and does these classification corresponds to the part of speech text like nouns, verbs, etc. So actually language models do something like that. There are some text, and there is an instruct to continue this text and or fill these gaps in it or do something with part of the text. This is how they were from the far perspective. A fun fact that the first large language model in history would be the Library of Babel, which is introduced in 1941. This is a theoretical project where there is a imagine library where there are rooms and you can go from one room to another, and there are books, and books contains all the permutation of each words in every length, and it's actually just like a language model but without weights. So it's unusable, but you can find every word if you know where to search for it. And this implies the quote that after reading the dictionary, all other books are just remixes. Fun fact for this is that the similar idea is the P5 system, when you can encode your data in digits, and you must know the right digit to start and the length that of your data, and you can encode any of your data in the P. Just have to count the digits that is required. So machine learning became something like this. You have the data, you put it in this file, and you steer it and do it again and again recursively until it starts looking right. And this is how prompt engineering works when linguists do prompt engineering. And sometimes I say that this takes too long and you should try other methods also. So how large language model affects typical task? This is a typical task for a language model: fill the gap. And I don't know how successful this solution is, but it works. Some more typical task for linguistics is the syntactic parsing. You know it from high school that you should the subject and the statement of the sentence, and it's very boring. And nowadays it's practically irrelevant because large language model doesn't do it, and it's technically already solved, and there is universal dependencies for it, and for it Hungarian makes 80% F score, which is not good, not bad, but unusable. And the problem is with the language and the linguist, but languages make better performance for it, and as I said, it's irrelevant because it doesn't need it by large language model. The backup task for this task, if you want more precision, the chunking for information retrieval, when you extract the fields that you want, but not their actual relations and not their inner structure. It's used for example, named entity recognition and information retrieval. And it's a supervised method. It needs a training corpus, and our observation is that generative models can do it without supervision quite good nowadays. So it's also a task that's not relevant anymore. There are the problem class of just give me the result, as I used to written text recognition, speech recognition, etc. And the large language models are fine-tuned for these tests, and the actual accuracy depends on how big and smart the large language model is, and how big and clean and I don't know the training data is. So it's practically solved because the nothing to do with these tasks, but the parts which are probably unrelated. and it's easy to create synthetic examples. For example, accent restoration. You take a sentence, remove the accents, and say to the model, do the inverse of this task, because it's far more harder than removing the accents, and large language model perform well also in this task. So if you are lazy and just don't put accents and type without accents, the large language models can help you. The greatest wish of all linguists is a solution, an ideal solution, which probably be large language model based, that can normalize text at least close to the ideal state, where linguists can handle corpora and not have to worry about the noise. Preferably in an unsupervised manner, because currently the rule-based solution requires a lot of manpower and very costly, and other methods are not currently known. So from the linguist's perspective, game has changed. There was a status quo of the hybrid methods where rule-based and statistic-based lived in a symbiosis, and this is broken. So linguists are left out from the game, and just the applied tasks are really used nowadays. No more post taggings for getting word classes, no more morphology, no more syntactic parsing, no more linguistics. There is a large evolution in the last years in unsupervised model, which will be very important in the next slide. Classical machine learning is cannibalized by these generative models. No one knows HMM, maximum entropy, conditional random fields, and those stuff anymore. We can't even remember of their names. They are all gone. And some of the past large language models too, because they are not so smart and not so large anymore, like the famous characters of Sesame Street, Elmo, Bert, and even ChatGPT 2, because ChatGPT 5 is on the way for release. So just they want some more money out of ChatGPT 4 before releasing 5. Only the symbolic methods survived where there is no enough data, why there is not enough data, and they are used for the over-specified problems, which is another class. It's something like that: solve this task, but I want to know, validate, control, customize, and do everything with it, and not just the result that interests me. Supervise the machine learning methods are expensive. They need a lot of human resources. No one wants to be an annotator. For engineers who have big salaries, and annotators have not big salaries. Linguists don't like to be second-class citizens. If you can remember from the 60s, there was the computers who was actually humans, usually black ladies who could count very fast and precise, not as the computers at that age when the numerical methods was in doing their baby steps, and they could simultaneously write mirrored to the glass, where from the other side the engineers could read it as in our modern computers. So no one wants to be like this anymore, and this is the motivation behind that industry moved into A/B testing for evaluation. But what will be done by science if industry doing two groups, and a control group and a variation group, and if something works out, then they change. If not, they drop the other group and try another variation. Some popular tasks like summarization can't even evaluated with standard measures. This is another challenge. And generative models are optimized to the output quality, and they make errors that are hard to spot on the output. everybody can write prompts, so everybody can pretend they know linguistics and know programming without even learning it. They can write essays and translate on the fly, so no one ever have to learn the language or research the literature anymore. And humanities and science need to adapt to this because most of the humanities exams are about writing essays. I already mentioned optical character recognition, which turns out good from this, and no one uses printed lexicons. As you search Google, use a prompt on ChatGPT and write on Stack Overflow, and but the good old lexicons couldn't be converted freely for linguists to use. And the interesting thing that language and cultures are very fragmented in humanities, but all of them are unified by this data science. The issues are the following: that not all languages are supported equally and correctly. Some examples like this, that of the machine translation, when the words are just used and not really, machine doesn't really understand what you want to say and your motivation behind it. So may I call you back is translated to szólíthatom hátsónak, like back, and lementem a boltba is translated to I save it to the shop, because lementem I save. It's a same form written. And rendezek egy bulit, mindenki elment is 1 week ago translated to everybody left, because mindenki elment could mean that, but I was to write that everybody came to the party. So it's the opposite what I wanted to say. So it's perfectly grammatical. It's hard to spot the errors. Not directly helps to learn other languages like we do. It's more like when babies learning their first language, and when there is not enough data, expert annotators, computational powers, money, you name it, you have to do it another way. Humanities are fragmented and mostly in this situation, so we don't know yet how to utilize large language models in a mess. Cultural heritage is most likely created in the digital age, harder to archive, more quantities created from day to day, and nobody wants to lose anything. And this should cost more money for everybody, but there is no money for that. Yes, we preserve cultural heritage for later, but when is this later? How much would it cost to make this later sooner? We don't have the money, so we can wait. And this is not good for humanities, because even after our deaths, we will wait for a better model to process this cultural heritage. There are legal issues, and I used to came up with the fruit of poisonous tree doctrine. When the tree is poisonous, then its fruit should be poisonous by transitivity. And from illegally gathered text, models that is trained from illegally got text should considered illegal, but it's not. This is an example of ethical issues. This for you, the left one is a first quarter journal in surface and interfaces, and the other is a fourth quarter journal. They've been using some large language model to write the article, the paper, and both papers are accepted. So the editors, the reviewers, nobody really cared about accepting these papers, and they are on the internet with these object identifiers. So conclusion, one have to sue big companies if you think that you has some text that illegally put in this language model, because machines don't read or write reserved statements that are appearing in every pages on the internet. They don't publish corpora. This makes hard for scientists to debug and examine these models. Corpora are growing, but their quality is not growing. But you can filter better quality subcorpora for it if you have the time. And the theoretical linguistics lose the focus, and applied linguistics like translation, summarization, and so on are in the focus. Maintenance cost and initial entry cost are very high for humanities scholars, at least. There are long answers, avoid the questions. It's like an oral exam situation, which we all very used to. And it's funny examples which I have no time to examine and speak about. And the funny thing is that large language models tend to give non-existing bibliographies, which people are given by their supervisors, and these bibliographies to the librarians, and librarians are plugged with these non-existent bibliographies generated by ChatGPT, and they have hard time to verify that it's actually a non-existing book. So some success stories. There is a Chango speech sound recording that cannot be automatically converted to text, but we are on the material. Nobody wants to be an annotator. There are official correspondence of famous people in digital editions released, which is has faster paced by large language models. Archaeologists can get really good use of 3D modeling and AI for assembling parts of stuff, and for example, language exams can perfectly good generated by this text with large language models for teaching. And of course, the spirit of the mechanical Turk invented by Wolfgang von Kempelen is with us, because the lead project manager of Amazon on the cashier-free shops said this sentence, that if you value a high accuracy, you must have a human reviewer somewhere in the chain. So it's like mechanical Turk. So your, how it's called, attention, and that's all.
Thank you very much. We have a short time for questions. Okay.
Thank you for the great overview. This is a very interesting topic for many of us. It's frequently coming up in discussions. I have an infinite amount of questions, so I try to pick the most interesting one. You have shown what has happened in the last 10 years. What would be your predictions where this all is going?
I predict that the next talk will talk about this.
So some similar question that you have, so the technology you have mentioned is the transformer models primarily have very severe limitations, and are there serious attempts to overcome these? I mean, in other direction, other methods, not the transformer, not so in the linguistics today.
Some new method that stems from linguistics,
which works for linguistic problems, but not based on transformer technology.
I think there are. I try to came up with one, but I'm not there yet. And from the data science perspective, there are also attempts to do something like this. as I said, they try to make more sense into vectors to give them a linguistics insight, but it's in their baby steps, so it's very at the starting phase.
Your question?
Thank you for the nice talk and proving us all unimportant in the future of science. Then what's the next task or the task or challenge that you would like to do, and you assume that ChatGPT won't do it in the next 3 years? So
I think cleaning the data is such task, because ChatGPT transformers and all the deep learning stuff works on noisy data, so they don't have to deal with cleaning the data, but it would be essential for linguists. And in this case, somebody can have a big amount of user base if he or she could come up with a solution that works for large corpora, for example, in a scale. I think Notabra would have examples that cleaner corpora, which are much smaller, can perform at least equally or better than the noisy corpora, but cleaning corpora costs more than the maintenance of the noisy corpora.
I have a question related to this one. So recently we have seen a talk at the it was a juristic or legal based something that's a more cleaner corpora. This is the first time I saw this verb, so no, I hope I understood. So where the logistics, where the proper words are kind of limited. So do you think that this level things can be work better and perform better than in like the everyday language what we are using?
Yes. For example, in our web harvesting project, we used to harvest web with something like this computational power and not very big machinery, as, for example, Common Crawl from Amazon do, and with much less noise. And the quantitative indicators of that corpus is way better than